All right. Good afternoon, everyone. I hope that you guys can hear me clearly. If you have any issues with audio or video or something, let us know in the chat. I will check the our chat from time to time, if not like real time. So say something in the chat, or you can raise your voice up. Um, Okay, so my name is Min-Soo Kang. I'm an assistant professor at School of Computing and also at the same time graduate School of Information Security at KAIST. So today the topic is Blockchain 101. I didn't make the title, Jason actually decided this cool name. This is, as the name suggests, this is going to be supposed to be an overview of blockchain. Let me start with this simple logistics for today. I will do my best to keep the time, so 2.5 hour lecture. Which means that we will end by 6:30. I may not be the best professor at KAIST, but what I do very well in general is to keep the time, so I will try to keep the time. Okay. And in the middle, because 2.5 hours is longer than most of the movies, so in the middle we will probably have a very short bathroom break, but not like a long break, so that we can finish by 6:30, so that we can all go out for dinner early. Okay, so let's start. A brief introduction of myself. I actually gave the same introduction with the same slide last week, but this time I want to say a little bit more about myself because this is my lecture. All the time is mine. So I do network security and privacy. So that is my research area, and that's my field of expertise. And one specific field of this network security and privacy is blockchain security. So since my students got interested in this blockchain space really heavily since 2016, I got involved in this blockchain space. And we've been publishing and working on a number of projects and publishing in this domain. So I do also do other projects like internet architecture security and 5G and 6G, wireless securities, and one of those fancy things. Among those projects that I've been working on in blockchain research projects, these are the list of several projects. I will, if I have chance, I will just try to mention a few of them, briefly mention a few of them in my lecture today. So, let me just say something about them. We have working on a partitioning attack against Bitcoin, meaning that we designed a attack tool that can actually carve out some parts of Bitcoin network so that they can be isolated from the others, and double spending becomes possible. And we wanted to build the partition resistant blockchain peer-to-peer architecture. And we have shown that low-cost eclipse attack, another form of partitioning attack in Ethereum, is also possible. So in those research, we actually found some vulnerabilities in Bitcoin and Ethereum, and we proposes some fixes, and some of the fixes are accepted by Bitcoin and Ethereum. Then they are running now in the Bitcoin and Ethereum. And we also did some mixing in Bitcoin, and we are trying to find consensus bugs in the Bitcoin and Ethereum implementations, because these days consensus implementations gets much more complicated than before. And and we're trying some other crazy ideas, like enforcing network service guarantees for public blockchains, not the other way around. So I guess that's give you a sense of what I'm doing and which layer in blockchain what me and my group and students of my group are mostly interested. So today, let's set this aside, and then today what we're gonna do is to have an overview of blockchain. So overview of blockchain. Let me start with this figure. I just borrowed it from Jason's last lecture. This is a very cool figure, actually. What I'm going to tell you about is the lowest level of all this stack. If you look at the bottom, I believe you see my cursor here. There's a blockchain, and on top of blockchain, smart contracts are running. Distributed file systems are not necessarily directly part of this blockchain, but some are using blockchain. And there's Oracle problems and whatnot and blah, blah, blah. So I cannot really touch all these topics. Really, I cannot really do that, but I will try to focus on the blockchain itself for today's lecture, 2.5 hours. And then next week, I am going to use half of next week's lecture time, 1 hour maybe, to briefly talk about, layer 1 and layer 2. Layer 1 refers to the traditional blockchain. So layer 2 is a more advanced topic, an emerging topic in blockchain, and which may sometimes include zero knowledge proofs. And so some of those advanced topics will be discussed next time. So in a nutshell, what I'm gonna do in this one day and the next week is to provide you some foundation of this entire Web3 stack from the up to the bottom, and I will try to talk about the bottom part. So actually, this morning I asked myself, should I really give this lecture to the audience who are gathered together here to create cool Web3 apps, killer apps? The answer might be no, because you can actually build cool Web3 applications without knowing anything about blockchain. You can start. Right. I mean, not all you need, but you can start with Solidity. You don't need to know about blockchain. Then why am I teaching this? So I think this analogy may actually work. So if you want to become a super good web application developers, system designers, architecture, then you can, I mean, okay, let's say, web developers, you can start with the web protocols and HTML and all sorts of interesting things at the application layer. You can start building new things, and that's totally fine, but you cannot be a great developers without knowing the underlying networking part of it. If you don't understand how TCP works, let's say how TLS works for encryption and decryption, and then your ability to to do a lot of cool things in your web applications may be limited, because in some cases you actually need to touch the lower layers of this and get your hands dirty to fix some problems when things go wrong. So from in a similar angle, if you know what is blockchain behind this all Web3 stack, then it might be helpful for you. For example, Jason mentioned last time that smart contracts, code that you are running for Web3 can be uploaded but cannot be changed. And it actually may sound weird if you are new to this field, but if you know and understand the foundation of blockchain, that actually sounds kind of trivial, right? So that kind of things, if you understand blockchain, then things becomes much more clearer. For example, some people complaining about Bitcoin being too slow, 10 minutes for one block and an hour for confirmation. Ethereum, 12 seconds for one block. I mean, why is it so slow? I mean, can we just make it 1 second and have a super cool finality? Why can't you do that? So that kind of complaints doesn't really make sense if you understand the blockchains, and fundamental conflicts and trade-offs made in those systems. So that is kind of things that I'm going to deliver you as much as possible in this limited time. Okay, so that is my kind of justification. Why am I giving this blockchain lecture to the crowd who wants to build Web3 applications. Let me start with this as well. Why blockchain? So I think I remember that Jason briefly mentioned that you can probably build a Web3 without blockchain. I mean, you can try. Yes. So let's think about it. If we really need blockchain. I actually like this flowchart really a lot because this was, oh, I forgot to mention the names. This was proposed by Woost and Gervais a couple of years ago, and they show that this might be useful for people who say that they're going to use Bitcoin, I mean, blockchain, for whatever application they're going to run. So let's follow from the start and then see if the application requirements of your application really make blockchain really necessary. The first thing is that, do you need to store states? If not, then don't use blockchain. So in many cases, you just go to don't use blockchain. You don't have to use blockchain. In many Web3 applications, I believe that you need to store states. So for this simple exercise, let us assume one application that Jason mentioned, those donation application for Web3, right? Then yes, we need to store some states because donation, the amount of money stored there should be some kind of states there. Okay, are there multiple writers? Yes, many people will want to donate, so it's yes, luckily. Can you use an always online trusted third party? If you're willing to trust this donation institution, whatever it is, then you don't have to use blockchain. But if you cannot really trust them, if you are willing to trust the code that they're gonna open up, then the answer is no. So we can still probably use blockchain. So following this, I mean, I'm not gonna really go into all the things. So then you can actually decide whether to see what you want is a public permissionless blockchain or public permissioned blockchain or private permissioned blockchain. So as far as I know, many of the Web3 applications do need blockchains. And that's the reason that we are going to talk about blockchain. And many actually requires permissionless blockchains, because not all the writers, who wants to change the states in the system are predefined or known in advance. So so enough of the justification. I kind of have to justify myself, why am I teaching this? So this is the agenda. First, we're gonna start with a very simple example, like digital currency. And historically, the whole thing started as a digital currency, and as the people wants to build the ECash, and that was the starting point, sort of. So we're gonna go back to that point and have some thought experiments to figure it out. Why is it really difficult to do that? Why is it so difficult to have a truly digital currency? And what properties should we achieve for that? And then we're going to move on to the Nakamoto consensus, which builds the Bitcoin system. So in other words, we're going to learn how Bitcoin actually solved the problems of the previous digital currencies and what kind of properties Bitcoin provides us. And then we're going to move on to Ethereum. And Ethereum is different from Bitcoin. There are many similarities. It is different. And the big difference is, one of the big differences is that Ethereum has a smart contract, and we're going to see why they are different and what is smart contract very briefly, because we will have a full session on smart contract in 2 weeks from today. So at the very high level overview, we're going to see what is smart contract and why that smart contract makes Ethereum as the world computer. So there are many things that Bitcoin cannot do, but Ethereum can do. So that it will be the topic. And the last part of today's lecture will be about Ethereum's proof of stake. So Ethereum used to have a consensus algorithm. I mean, we're going to define what is consensus later, but consensus algorithm, which is the core of blockchains algorithms, similar to Bitcoin. So Nakamoto consensus and Ethereum consensus were kind of similar, but now it's totally not very different. So we're gonna, I will walk you through what kind of changes they have made and why, and what is the implications, and what is the current status. Okay, so understanding all these again may be an overkill to some of you guys, but I believe that it will be helpful for you to develop Web3 applications. And then next week, we're going to have some more discussions about the advanced topics. If you have any questions, then feel free to say anything in the mic through your microphone or in the meeting chat. All right, cool. So I need to first say upfront that many slides that I'm going to use are borrowed from good researchers like Pratik Saxena, one of my old colleague, and Dan Bone and Ertam Nusretas. Actually, he's a PhD student, so and I just borrowed many of those slides for the purpose of showing you a good animations. So I used to build my own slides for those things, and last year I realized that I found that other good researchers actually has built super cool animations, and that helps a lot, really. It's really helpful for students to understand the those mining activities and blocks and move around. And so yeah, I kind of gave up. Their animations are so cool, so I just borrowed many slides from them. I really want to thank them, and then say this up front. Okay. Let's think about these online transactions. As I said, online transaction, or ECash, was really one of the most earliest motivations of having transactions on the internet. So physical cash is non-traceable mostly, and is secure also mostly, because you can copy cash, but it is detectable mostly. And low inflation, there's a good system probably. And but the thing is that you can't really use it online directly. So instead we were using electrical credit and debit transactions. So people really always wanted to have this ECash, which is secure, single use, no double spending, and super reliable, low inflation, and privacy preserving. Your government should not be able to trace whatever you're doing with your ECash. So was it successful? Some success stories were found even before Bitcoin. For example, David Chaum invented a blind signature scheme in 1982, long ago, really, for ECash. And 88, retroactive double spender identification was developed, and other things, were all continuously developed. And some version of ECash even was tried. But the major drawbacks of all the ECash before Bitcoin was that they needed some sort of trusted central party. So their eCash, you don't really trust the bank completely, but you still need to trust at some part. For example, using blind signature, your bank should still write a certificate for transactions. So the notion of bank or centralized trusted third party is still there, and it's completely expensive and etc. So that's why it didn't really fly. So it all started with Bitcoin, as everyone now fully aware of now. This was a distributed, decentralized digital currency system. Distributed, decentralized. So we're gonna have some discussion of what that really means later. It was released by Satoshi Nakamoto in 2008. Effectively, a bank can be run by an ad hoc network. So there shouldn't be a notion of bank, but an ad hoc network, a bunch of random computers on the internet can form a peer-to-peer network and try to run a consensus algorithm and make some agreement so that the result can become a bank, right? So digital checks, transactions can be made, and the bank can actually certify that. But without a bank, we don't really have a bank. Ad hoc network can become a bank. A distributed transaction log or a append-only ledger can be formed. So Bitcoin in this sense is really a super big innovation. We're going to have some more discussion about Bitcoin. I'm just pointing out that historically Bitcoin is the very first of the real ECash. But Bitcoin was not created out of thin air. Really, there had been a chronology of ideas that existed even before Bitcoin. So, for example, this was nicely illustrated by Narayanan and Clark. So from the early days, like 80s, Mercury is a very nice way of creating highly efficient verifiable logs. So cryptography has been preparing for Bitcoin in some sense from long ago. As I said before, digital cash like ECash, people were discussing about it in the 80s. So everything actually was kind of invented, or people envisioned this kind of thing in the 80s. And proof of work, it kind of was invented in 90s as a solution to spam mails and denial of service attacks. If you force people to compute many hashes, then you can actually deter them. So as a good solution to denial of service, which was not really used heavily for denial of service defenses, but now for Bitcoin and other cryptocurrencies. Byzantine fault tolerant, and in the distributed community, distributed system community, they've been talking about Byzantine general problems, when two are not trusting each other, and communication channels are super shady, and how do they get to the point where they agree on something. So this is actually the core the property that the blockchain system really wants, and the notion was invented in the 80s. And as I said again, Chaum's cool tricks were invented in the 80s as well. So it has a long history. And that's why many computer scientists and now they actually revived some of these old ideas and then apply to blockchain, and that's very cool to see that. Let me start with this very simple scenario, which is self-regulating currency. So we want to let's assume that Alice and Bob and Charlie, those three people, have some coins, and they want to have this currency, the notion of currency, and it has to be self-regulating because they don't want to get the bank involved in the middle. I mean, if there's any bank in the middle, then there's no self-regulation. But let's see if we can do that, and with what technology and what property are really desired in this simple experiment. So Alice may want to send something coin to Bob and Charlie to Alice and Bob. So let's see, there are some transactions, the movement of money from Alice to Bob, Bob to Charlie. And if these two transactions are made in this order or even at the same time, it's okay. And maybe Bob wants to send this to Charlie, and Alice may want to send her coin to Charlie, and that is also right. Okay, it is acceptable. But if Alice is trying to send this coin to Bob and Alice wants to send the same coin to Charlie, then this shouldn't be allowed. So this is what we call a double spending, and this shouldn't be allowed, right? I mean, this is touching the core security of currency, digital currency, or even just currency. This shouldn't happen. One solution is to use a bank, but in a more transparent manner. So you can send your transaction to the bank, and as you do that, the bank promises to have a public ledger. And this might be a good idea, because this way you can probably get away with this double spending problem. In other words, if Alice is trying to spend her coin twice, then Bob or Charlie will be able to see that and see that Alice is doing that. So that is cool. If we push this idea a little further, we can probably have this idea of public append-only ledger. So the append-only ledger part is important, because this really means that once something is written in the ledger, you cannot change that. So yeah, if that property is guaranteed by the bank, then we can probably use it to have the self-regulating coin idea. Although we're involving bank, but we're involving bank only for this, for the management of this ledger. Let's see if this can be a solution. So, but as the title says, it's almost a solution, not really a solution. Let's see if this can be useful. This is actually useful. You know, having a public append-only ledger is very useful, because anyone can verify, as I said before, that Alice has enough balance, right? If you look at all the history in the public append-only ledger, then yes, you can check that Alice has this certain balance. And then you can also check that she authorized a transaction to Bob. How do you do that? You can check that this ledger includes Alice's digital signature. So we're going to talk about digital signature very briefly later, but it really means that once the Alice writes that, then it means that Alice actually wrote it. And new balance is and also credit debited correctly, you can check it through the ledger. So for example, Alice digitally signs, I want to pay Bob $45, then digital signature provides you authenticity and integrity, meaning that it came from Alice. And also the message here, I want to pay Bob $45, hasn't been modified. That's good. And also Alice publishes her public key, and then so that anyone who is seeing the ledger and her public key can check that this came from Alice. And when doing this, Alice doesn't have to reveal her real identity, because she's only revealing her public key. She keeps her private key secret. So if this is the operation, then yes, this may actually work. And if this is all you need, if this is all you want, having public append-only ledger, you don't need a blockchain. You really don't need a blockchain. There are some ways to achieve this public append-only ledger. For example, DNS, DNS ecosystem, they have been having this certificate authority, which uses a public append-only ledger, but it doesn't use blockchain. It uses a number of non-colluding parties that provides and monitors and audit this public append-only ledger. So blockchain is not needed. So then we don't need blockchain, then is that all? Of course, there's some missing things. There's a problem with it. So what is the difficult? I think that the title is misleading. So what's the problem of this public ledger or public append-only ledger? One problem is that it is difficult to provide the correctness of the distributed append-only ledger. So first thing is that if a bank is a single entity who's managing a single public ledger, then you should be worried, because if the bank goes down, or the public ledger goes down, the server goes down, or even the entire data center goes down, then your money's gone, at least unavailable for some amount of time, which is bad. So it has to be somehow distributed. This is a must situation. Then if the ledger is distributed at, even two public ledgers in the West Coast and East Coast, maybe in Asia, in the US, you still need to guarantee that they are the same. And that is difficult. That is a difficult job to actually achieve. And also, another thing is the censorship. How can you really prevent the censorship, or at least mitigate the risk of censorship of transactions? So for example, if, let's say, bank operator is not doing anything but to maintain this public ledger, but bank somehow hates Alice and prefer Bob, then bank can seize the Alice transactions and try to drop it, or do something else as well. And that is bad. And this actually becomes a more and more problem, because sometimes the order of the transactions that you are putting into the ledger becomes a huge difference, at least some difference. So you should be worried. We should be really worried about that. Even the bank or someone who's managing the public ledger, or even the network in the middle, can drop or delay the transactions or swap the order of the transactions that goes into this public ledger. So, so the message here is that public append-only ledger is really, really good. It's almost a solution, but it's not really a solution. So then what is the solution? The solution should be a state machine replication. So state machine replication is a umbrella terminology for any algorithms that replicates the states of a machine. In this case, our states is the transactions and the balances of those people, Alice and Bob and Charlie, okay? And they have to be replicated for the reason that I already explained. Has to be replicated, otherwise, it is unreliable. Earthquakes, fires, all sorts of wars, these happen. So it has to be distributed for reliability. It's a must thing. And when you do that, when you distribute it and when you replicate your states, they have to be synchronized well enough so that you have a guarantee that if you put in your transaction, let's say Alice put in your transaction into the system, the ledger, and it is going there without any problem, without any induced delays. Bob also should be able to get some guarantee. And what they want is the final states that is agreed by those nodes, distributed node in this state machine replication systems, that says that this is the order of transactions that they decide, and that is it. So in some blockchain terminology, you can say it's a confirmed transaction blocks, but you can think of it as a ordered list of transactions that these committees or miners, I think I have an animation here, yeah, those replicas or miners or validators, in different contexts they are called in different names, but those independent machines that replicates the system, they need to agree on that. 잠깐만요. 제가 지금 수업 중이어가지고요. 네, 죄송합니다. Sorry. So they need to agree on that. These are the list of transactions, and that is the order. So that's called total ordering, and total ordering should be agreed by different nodes. So that is the problem that we really want to have. And again, let's go back to this bank scenario, who is a single entity or multiple entities, but whose job is to have this public ledger, public append only ledger, which is cool, but it doesn't really provide that properties, because any, creepy banks in the middle can change the order, and then they disagree on the contents in the public ledger, and then it becomes a big problem. Now this entire system, should stop. So the goal of consensus, in the sense that is that we want to have this transactions that is ordered in time, and they are grouped into the data structure called blocks. But again, you can think of it as a long list of transactions. So for example, like, for example, in the Bitcoin, every 10 minutes, new block is formed, and in each block you have a list of transactions. And again, the order really matters. And this order is agreed by the node in the system. Okay, some may want to switch the order, but if, let's say, the majority wants this way of order, then this will become confirmed. And now the blocks are totally ordered in time, and anyone can verify their order. So we'll see how Bitcoin actually achieved this in the later part of today's lecture. I'm just before we are going there, I want to touch some of the high-level properties so we want to achieve. So again, what we want, but is difficult, which is difficult, is to have this agreement over transaction ordering. Yeah, I think I already said it, but if Alice is making two transactions, let's say sending this to Bob and Mary, which shouldn't happen, then this order becomes super, super important. Why? Because let's say there's two options, two possible orders of transactions, one on the left-hand side, one on the right-hand side. Depending on the orders, the Alice coin can go to Bob or can go to Mary. Because if the system agrees that the later transaction that tries to spend the already spent money will be invalidated, then the result will be very different. So the order is important. So order is what really matters. So then, what is the blockchain? Let me check the chat. Oh, no question. Okay. If you have any question, please let me know. By the way, I found this giving an overview blockchain lecture to almost any audience is challenging because some students have very good background in blockchains already, maybe know better than me, but some don't really have any background. So I need to sort of, give up some audience. So in this case, this is a high-level overview. Okay, so abstract answer to this, what is blockchain, is that the blockchain provides coordination between many parties. You've seen the many parties, like, right? Those small computers, replicas, miners, validators, whatnot. They, they are many parties, and there's no single trusted parties. If there's a single any trusted parties, then yes, we don't need a blockchain. And for financial systems, we really need sometimes we want no trusted parties around. So that's why sometimes blockchain really fits well for financial systems. And that's probably the reason that Bitcoin was the very first blockchain application, cryptocurrency. So so what is the new idea then? How Bitcoin solve the problem of state machine replication. So in 2009, Bitcoin came out with several innovations. One is a practical public append-only data structure. Right now, we all know that public append-only ledger would be really cool. But that's not all. It is secured by replication and incentives. And it provides a fixed supply of asset, Bitcoin, BTC, and digital, which can be used for digital payments and more. Ethereum came 6 years after that, and it added some more innovations on top of Bitcoin in some sense by providing a blockchain computer, which we will see later. And now we're seeing more and more innovations, and which will come later parts of today's this semester. So in the consensus layer, in other words, the main functionality, main feature of blockchain for the state machine replication is to provide these properties. And we should actually understand that different blockchains provide different properties. They provide some basic properties, but their properties are slightly different. Sometimes, some blockchains give up some properties over others. So understanding those slight or subtle differences actually matters in practice. But in general, consensus layer of Bitcoin is try to provide persistence, which means that once something is added to the append-only data structure, data can never be removed. So you can say immutability. Safety means all honest participants have the same data. And you can see that from the very beginning, people have thought about dishonest participants, right? Because this is it's going to be a financial system after all, so the dishonest participants must be there. We should assume that. Liveness means honest participants can add new transactions. Okay, if system stops, you cannot really add new transactions. That liveness is gone. Open, anyone can add data, no authentication. So openness is not the necessary property for all blockchains, all consensus. Some blockchains do not provide openness; they are closed. Not all permissioned networks are closed, but so it differs. And for the purpose of today's lecture and probably this entire semester, we're gonna be talking about open system, because Web3, we are typically talking about open system where user base is very large, and that's I believe we are our target applications. I received one question from Donghui. What's the difference between liveness and openness? Liveness means that life should go on. The system should operate, move on and move on. Okay, so you can define liveness for a closed group of users or open group of users. Okay, and openness, and it's different. Anyone, so the open system allows anyone can add data. Anyone. So in for example, Bitcoin, anyone can just create their own account address and then start to create transactions. And some other networks may have a closed group of users who can do that. And so that is the main difference. Okay. Yeah, thanks for the questions. So if you have any questions, let me know. Another question: if the data can never be moved, then isn't there storage issue? Oh yes, storage will grow. It will only grow. And can we reset the storage and then decide that all last year's storage goes away and we should reboot it? No, you cannot do that, because in order to know the history of it, you need to know. So there are some ways to handle this, but if you really want to prove the correctness of any account by yourself without trusting anyone, then you need to have the entire storage from the beginning till now, and this becomes a storage issue. Yes. So that's because that's why it becomes more expensive to run the blockchain network. But since more and more people wants to use blockchain, the blockchain becomes really the pipelines of this entire economy. Then it becomes busier and busier. And there's a storage issue and a cost issue. They are also, they are like interchangeable thing. If storage issue, then it's expensive. So that's why people are starting to talk about another layer on top of this extremely busy and heavy blockchains. So we're gonna be talking about that next week. Distinction between so Minkyu asked this question: the distinction between openness may lead to public, consortium, private chains. Yeah, there's a different notions like public chains, consortium chains, private chains. Public chains, everything in the ledger is visible to any others. Consortiums, it is the ledgers can be maintained by the consortium members. I guess we can also define two different parts, types of consortiums. In one, all the ledgers can be also private, and ledger can still be public. Private chains is just totally private chains. So I think different people use different words. But that's my definition. Okay, Chamin asked this question: if data can never be removed, or data can be revised? So that's a good question. Data can be revised. Typically, no, you cannot revise the data. There has been some proposal that we probably need to allow the blockchains that was, the contents written in blockchain should be revised if we had enough, a consensus after the fact. But in general, it cannot be revised. So that is the notion of confirmation and finality, meaning that once it's written in the blockchain, then it is final. You cannot really change that. And that may give you some concerns, because if I say something stupid by mistake, then, I cannot change that. But it also gives us very good assurance that if I really paid for my tuition for the next year for this university, and then that is written and accepted and confirmed and even finalized in the blockchain, then it is really finalized. There's absolutely no way, no one can change that. So that gives you a good assurance, that good security. So I think that's the two sides of the coins. Okay. But there are some ways to upgrade what you have written in the blockchain. I think that will be some more about that will be discussed later part of this course. Okay. Yeah, thanks for the questions. There are some other desired properties, like fairness. Your confirmed blocks are proportional to the computational power you have connected, in the context of mining, right? Proof of work, which we're going to talk about later. Throughput, lots of transactions per unit time is desired. Latency, short time frame to confirm a transaction. This is a very critical thing, especially for financial applications. Typically requires 1 second confirmation or 1 second finalization. And anything longer than that is something people hate. And decentralization, large number of miners proposing transaction blocks. So this is also important. Even if everything is so cool and good, your system is highly centralized, and then you can't really you cannot really ensure the high reliability of your system. So there are many properties we want blockchain system to have for this single application. what was the application? Self-regulating currency, right? Even for that simple application, we need to achieve these many properties so that we can actually have a self-regulating currency. And let's see, using this cool animation that I borrow from Dan Bonet's slide, see how our blocks are added to the chain. So without giving too much of detail of Bitcoin yet, let's see how in general in blockchain we are adding blocks and transactions. So there are different people, Alice and Bob and Charlie, and they sign their transactions and send it to the set of miners, validators, or replicas. And then in this animation, you see that one of them are saying that I'm the leader. And then the leader, package them in the data structure called block, and then upload it to the blockchain. And in return, it receives some reward. And others verify the block and saying that, hey, I've seen those transactions, and also the order is okay. So that's a verification of others. And this makes sense because the very action of proposing this block, which has multiple transactions, and having others to verify that this already achieved the form of agreement, right? They all agree on that block. And the order was decided by the leader. And another set of transactions are made, and the next time another guy becomes a leader and he posted it in the blockchain, and this goes on and on. So this sounds cool. This may sound like that we are achieving this state machine replication for transactions, but not quite yet, because consensus is really a hard problem. Let's see why. There are 4 miners in this example. There are multiple transactions, 1, 2, 3, 4. And since those 4 miners are different entities, they cannot be a single entity, because if it's a single entity, then you can't really trust that single entity. So they must be different entities running in different locations, typically in all different geographic locations. Typically in Bitcoin, you see 10,000 or 15,000 such node running across all parts of the world. So when transactions are made at certain point on the globe, some receive these transactions earlier than others, and the order can be different. But if in the good case everyone agree on the order, yes, they may have the same copies, are in a consistent manner in the exactly different same order. But there are network delays. They are in different locations, some in Asia, some in the US, some in Brazil, then lots of delays. And this affects the TX transaction orders. So different miners will see different orders. I mean, they're totally benign. They didn't mean to change the order in any arbitrary manner, but the order they see is different. And as we discussed and as I explained with a simple example, the order matters, really. The blockchain is trying to decide the order. I mean, you may think that, hey, this is just an order, right? I mean, who cares? No, order is what we care. That is really the essence of consensus. So orders are different, then this is a problem. Somehow they have to come to an agreement to a single order. And also network can experience partitions. So sometimes networks just don't work, and some catastrophic events like earthquakes, and then they see different set of transactions. And also sometimes some miners may die, then it happens to receive transaction 3, and it never had an opportunity to share this information to others. Then all others see all the other transactions except transaction 3. So transaction 3 is forgotten. So that becomes a problem. Also, so far we've been talking about benign but unfortunate events, but sometimes some of them can be malicious. If they are malicious, they can say anything in the network. They can say even lie to others. They can even delay, drop messages. So that's why this is a hard problem. Let's go back to this thing. When everything is works well, they're sending it, and one leader is selected, and then nicely propose it, and everyone is like okay with it, then it's good. So if everything goes well, then we don't need to invent a serious blockchain. So let me briefly, maybe in about 10 minutes or so, to overview what is Bitcoin and what Bitcoin has done and why is it good and how it actually achieved those properties that or solve the problems that I mentioned. In order to understand, how Bitcoin really works, we need to understand three things at least: cryptography, and distributed systems, and economics. So all three really matters. And let me just go through this super quickly in a highly superficial manner on purpose. Um, so what we use a lot in blockchain and probably for your Web3 applications is cryptographic hash function. You may be familiar with hash function if you have taken any data structure, because hash is useful for building a data structure. But I mean, even search in many places. But cryptographic hash functions are different. Cryptographic hash functions guarantee certain properties, which I will explain later. But hash function basically takes any arbitrary length of input and it outputs a certain fixed length output. We call it hash value or hash digest or just digest or simply hash. And yeah, it's a short value, sometimes 256 bits or 32 bytes. And typically we put a lot larger input to the hash function. So that is a hash function. Then what makes cryptographic hash function so unique? Cryptographic hash function has this property called collision resistance. Collision resistance says that if let's first define a collision. If there are two inputs, x and y, they're different x and y, and then you put x into hash function, cryptographic, hash function, and y into the hash function, and their output is the same. So their output or hash collides, and this is the collision. And if you think about it, the input to the hash function can be much longer than actually it can be any arbitrary length, so it can have infinite space of input, but the output space limited because it's a 32 byte or 2256. I mean, depending on the hash function that you choose, limited length. So which means that there must exist many collisions. In other words, if you take any x for this, then you should be able to find y that causes a hash collision. Now, the cryptographic hash functions provides this property that is called collision resistant, which means that it should be hard, almost impossible, to find even a single collision for H. So that is it, really, So if this doesn't make sense to you, then think about it later. But just trust me, and this thing exists, and we use it all the time. And so whenever we use hash function, and in the context of blockchain, we implicitly, means that we are talking about cryptographic hash function, which provides collision resistance properties. So why is it important? I memean, one example is that SHA-256 is it's a SHA-2 algorithm. SHA-256 means that its output is 256 bit. This was the hash function used for Bitcoin. So whatever you put in, and then this SHA-256 function will output 0101 bit, which has a length of 256. Okay, and it is very, very difficult, almost impossible to find another input that gives you the same hash. And the hash is used significantly for most of the blockchains for the purpose of verifying contents in the data in blockchain in a highly efficient manner. And Merkle tree is one super important innovation that is used in almost all blockchains. So I am not going to go into any of details actually, but just to try to this, figure, because you sort of need to understand and at least feel the coolness of this Merkle tree. So when you have multiple like inputs that you're gonna put into this blockchain, let's say, blocks. So you can think of it as M1 to M8 as transactions, different transactions. And you want to have a one short commitment of everything. And you can actually hash them all together in a hierarchical manner, in a recursive manner, until you have a single hash, which is, again, 32 byte. So H is a very short hash, which actually sort of represents all the transactions in the middle. So and you can represent any number of transactions, and the number of hash operations is quite efficient because it's log n complexity. And so this is very cool. So in practice, if you place H, the top one, only the H in the block, then you can actually later prove that certain transaction is included in this block very easily and very efficiently. So hash is so important, and hash is also important for linking blocks. I think I don't have a slide for that, but all the blocks are linked together to previous blocks. They include the hash of the previous block, So some people, so the hash is really the essential thing that you need to understand, and along with digital signature. So in the early days of cryptocurrency, people used to call it just crypto, and then real cryptographers actually hated that, because all the cryptography used in blockchain and Bitcoin is just hashes, and it's not really a real cryptography. But so it means that it's that important. Cryptographic hash is super important. So if you have to know one crypto for your Web3 applications, it needs to be hash, cryptographic hash, and signature. So digital signature is very close to the physical signature in the real world. By writing a signature to a check, let's say, Bob agrees to pay Alice $1, then by signing it, you're binding this transaction to the author. Who's the author? Bob. So Bob should be the signer of this transaction. And once you digitally sign it, then it really means that Bob is the one who signed this. So, and you cannot really change that. In the digital signature, unlike the physical, signature, you cannot really change the contents of it. That's a very cool thing about digital signature. And again, I'm not going to really go into any of details here, because it's not meant to for this lecture. But one thing you really need to know is that if Bob signs it with his secret signing key and then give it to any others, then any other can verify the fact that it is Bob who signed this message using the public key of Bob, given that the public key, the authentic public key of Bob is available for the verifiers. And in most of blockchain applications, public key of Bob is actually, or is some form of the wallet address of Bob. So this public verification becomes very easy and very reliable. Yeah, let me just skip this. So so how do we use this signature? I think this is self-explanatory, but individuals in the system who wants to send a transaction and will create a transaction data and then sign it with their own secret key or private key. And the miners in the system can verify the fact that it is the actual authorized user who actually signed this signature, sent this message. So anyone can just verify it. So these are the two things, hash and the digital signature that you should know to understand Bitcoin. Now let's try to understand Bitcoin. So, or Bitcoin's consensus algorithm. Now you understand the signed transactions. People are sending signed transactions to the miners in the Bitcoin P2P network, and when they do that, they are doing this through the peer-to-peer network of Bitcoin, which I will explain in a little more detail later, but just assume that they are super well connected to each other. So one of them received this transaction and they will just broadcast it. We call it a gossip protocol. So they're gossiping about the information they received. And so that every miner can validate the received transactions and store them in their mempool. So, those transactions that are not on blockchain yet, but they have just received from others. So we call it a mempool. So they are maintaining these different mempools. There may be some differences in those mempools, but some differences are okay. So what's the new thing and cool thing about Bitcoin is that in every about 10 minutes, each miner creates a candidate block from the transactions in the mempool. And now the random miner should be selected. Remember the notion of leader. Now they have to be selected. But how they are selected. And we're gonna see in the next slides. Well, once the leader posted, and then it will be posted, and then they will receive the reward. So now up to this point, you already know that. And I think yeah. So the properties, I think we already have discussed that. So all those blocks are linked together, as I said before, linked through hash. The previous block's hash is included in the current block, and the TX root of this block includes acts as a commitment for all the transactions in this block. And so its header is very tight and concise data structure. Let me just go to the mining. Yes, so mining is the heart of this Bitcoin consensus. So now the notion of mining is to create a new block as a leader. Now miner must find a nonce such that the hash of previous block and the transaction root, all the commitment of all the transactions that you decide to include in this block, and a nonce. Nonce is just a random number that you choose, and the hash of it has to be smaller than certain target value. And this target value is a quite small number, and it gets smaller and smaller, so that it becomes harder and harder to find a nonce that satisfy this. finding this nonce value is same as that you are actually authorized miner to create this block this time. So the difficulty really matters, but difficulty is actually quite big, so that the target value is pretty small. So let me see if this animation, yeah. So if you find a nonce that satisfies this, then you can actually propose a block. I think we have this animation here. Yeah. So there are different miners, and this time this miner luckily working very hard, computing hash so aggressively, and find the nonce that satisfy this difficulties, and then it publishes that block to many others, and everyone will accept it because they can actually also check the validity of it by looking at the nonce and recompute the hash, and also looking at the contents of the block. I mean, the transactions in the block. If there's any double spending, then there will be some will say that something's wrong and I'll reject it. And if the most of the rejected, then it won't be included in the block. So, and then next round, some other miners got lucky and then, were able to mine a new block and attach it to the previous block that the previous guy mined. So this is the essence of mining, Bitcoin mining. And I think I received a question. No, it was not really a question. And the difficulty is adjusted every 2016 blocks to match the changes, to take into account for the changes in the hash rate or total amount of hash power that exists in the network. Yeah, the details are there, but that. So in Nakamoto consensus, simply at any given time, each honest miner attempts to extend, meaning that the mines on the tip of the heaviest or longest chain in its view. So because it's a chain with the heaviest or longest length has accumulated the highest difficulty for confirming the transactions in that branch of the chain. They want to extend the heaviest or longest chain, and that is really the core consensus logic in Nakamoto consensus or Bitcoin consensus. And the confirmation rule here is that each miner confirms the block that is k dip within the longest chain in its view. Let me see if I have a figure on that. I think I don't. I think I will have later, but I will explain it later. But typically, in Bitcoin, you need to wait for 6 blocks, which translates to 1 hour, to confirm your transaction in the block. Why? Because 6 block now, then if you compute, then if you calculate it, then it becomes nearly impossible to revert back your transactions after your transaction is buried in the 6th depth in the chain. So one important thing is that we're talking about confirmation in Nakamoto consensus, which is different from finalization. And one big difference between Ethereum, the try to record. Okay, cool. All right. So something is missing in the middle, but it was a very brief moment, so we should be okay. So Nakamoto consensus, just one good thing about Nakamoto consensus. So we've been talking about this, how to select the leader, right? Which makes sense. The one who work more and maybe a little bit of luck will be chosen as a leader, and then who can define a block, which is all about the order of transactions. Okay. Another super cool property that Nakamoto consensus gives us is this. Let's say that at some point, many miners are just, go away, and previously we had 8 miners, now 4 miners only. Then what happens? Do we have a problem? Does the network stop because we don't have enough members? Let's say, we decide to, have a consensus with 5 miners, so at least 5 miners. Now we have 4 miners. We cannot really make any decisions. No, in Nakamoto consensus, it doesn't really matter. Individually, independently, they work on the hash problem, and whoever solves the hash problem will become the next leader. And then this goes on. So this is called dynamic availability. The system becomes available in any case, actually, in any dynamic network situations, in asynchronous situation, even network is got partitioned, the network is, Bitcoin is available. So in this example, when k is equal to 2, then everything, behind equal to 2 and beyond it is confirmed. So in the consensus of in the internet setting, this is what we want to achieve, especially if we want open participation. As I said, there are non-open blockchains, but for the purpose of this course, we're going to focus on the open network. If you want an open participation, then we need to have this Sybil resistance. So I actually didn't tell you what is Sybil, but Sybil nodes are the nodes in the system that was created by a single entity. So it was a single entity, but single entity create many other nodes to pretend to be different identity, or many different identities to take over the protocol. So there must be some potential, protections for against Sybil. And so we want to have this Sybil resistance, and proof of work nicely handles that, because in the proof of work, Bitcoin's proof of work system, what really matters is the power, CPU powers, basically. The hash power, the amount of hash work that you can do per unit time is what matters. So identity is not really a big deal. So Sybil is handled. And dynamic availability is another thing that we want to achieve, and Bitcoin nicely handles this, because all the miners has to do is to work on the problem in the local setting. They don't have to talk to each other. They don't have to send votes to others. It's super simple protocol. What about the security? Can we show that Bitcoin is secure under synchrony against Byzantine adversary? Byzantine adversary meaning that a miner can do anything. What would be the best possible resilient? So typically we say that Bitcoin is secure if the number of malicious guys or Byzantine adversary is less than 50%. And I think this is sort of easy to understand. So let me just explain this slide and move to the next one. But let's see, what happens if adversary has more than 50% of hash powers. Let's say there's a block is confirmed, k is equal to 3 in this example. Adversary with more than 50% of hash power creates this block, but it's not revealed to the public, meaning that this block is created, but adversary don't share this with benign miners. They share it within their own colluders, but don't do it with others. Then all the benign miners will mine on top of that publicly known block, and adversary will mine its own fork, if you will, again. And since adversary has more hash power than the sum of all the benign guys, then adversary will have better chance to actually have a longer chain. And then when the attacker just releases it, then since Bitcoin follows the heaviest heaviest chain or longest chain rule, that selects the chain. So all the blocks, benign nodes blocks, TX1, TX4, and so on, will be removed and ignored. So this is the security of Bitcoin, meaning that if the attacker has more than 50% of the hash powers, an attacker can, sometimes people say that attacker can do whatever they want to do, probabilistically, and this is the reason. And when people are talking about the security of blockchain, let me just skip. They often forget about other attacks. So let's see, and they often ignore the network aspect of the security of Bitcoin. So let me try to explain in this figure. By the way, this was published in 2018. And then this research showed that Bitcoin security actually depends on the network latency of the Bitcoin network itself. So this 60, I think, yes, we have an animation here. X-axis shows the block time in terms of network delay. In this case, if I remember correctly, since this is a 60, the network delay is set as 10 seconds, meaning that all the Bitcoin nodes, when the new block is created, right? Then the time the new block reaches all other miners takes less than 10 seconds, which is reasonable assumption. Okay, then 60 means that the average block time compared to the network delay is 60, meaning that average block time is 600 seconds, which means 10 minutes. So that's where Bitcoin stands right now. So if you consider a delay attack and consistency attack, which is a known attack before, then let's make it simplify. Let's simplify it. Let's consider delay attack only, which is a well-known attack. Then Bitcoin is pretty secure because attacker has to have slightly more than this line of percentage of the node mining powers, meaning that 50%. So 50%, more than 50% is required for the miners, for the attacker to disrupt Bitcoin. That still makes sense, which is good. Okay. And again, why this is possible? Because Bitcoin's block time, average block generation time, is 10 minutes. Very, very slow. And so Bitcoin intentionally choose, when they designed the whole thing, they intentionally chose very long time between blocks, so that attacker has to have 51% of the hash powers to subvert anything. Look at Ethereum. Ethereum's case, it's about 1 point something. Why? Because Ethereum's average block time is about 12 seconds, and network delays for Ethereum and Bitcoin is the same, because they are using the same internet. So it's the block time in terms of network delay is only about 1 point something, and at this point, if the attacker is mounting a delay attack, then attacker can will need slightly more than 40% of the mining powers in the system to subvert or to change some values in the network. So proof of work, so in a nutshell, proof of work is good, is cool, and it makes sense. It gives you a pretty good security, meaning that attacker has to have 51% of the mining powers. But that is given that the average block time is much, much larger than the network delay. And why is this the case? Because network delay is bigger and bigger compared to the block time, then every time new block is created by some of the miners who luckily solve their puzzle, and the chances are that there are one or more or two or three miners who have the next blocks almost at the same time, and those blocks should travel across the world, literally world, through this P2P network, and that becomes a chaotic scenario where a single block is extended by so many other blocks almost at the same time. So that's a waste of time, and the attacker can exploit that. So that's roughly the story of Bitcoin's security. And one thing that we haven't really discussed yet is the one layer below this peer-to-peer, consensus layer. So we've been talking about this miners, right? We always look at this figure of miners and we always just assume that they are all distributed in different ways and they are all nicely connected to each other, which is true. But how they are connected? They are connected through peer-to-peer networks. So it is the part where you actually see the decentralization in blockchain. So in any system that we are using, we are using Zoom here. Zoom is a centralized system. All the servers, Zoom servers, is in some parts of in Asia, I think, in our case, and they are sucking all the video traffic and audio traffic and then rebroadcast to you guys. So that's what they do. But in Bitcoin and blockchains, if you actually look at their peer-to-peer communication network, then they are all in different locations, which actually is really cool if you actually look at it, and this is fascinating. Bitcoin, for example, typically 15,000 nodes are connected to each other, and this is the Bitcoin network, some illustration of the Bitcoin network. There are some nodes that are mining, the yellow ones. So some of them are creating a mining pools, and some are solo miners, or some are just a full node that receive and forward messages, but they don't mine at all. So this is the actual nodes in Bitcoin, and we have 16,000. It's getting larger and larger actually. 15,000 reachable node, meaning that they receive connections from any others, and there are several orders of more, at least one or two orders of more Bitcoin nodes that are just connected to those reachable nodes. So it really forms a large peer-to-peer network without any centralized party, and which is actually really, really interesting subject for research, because it is really the largest peer-to-peer network, man-made peer-to-peer network existing in the world. So with that, I will try to kind of summarize Bitcoin, but with this question, is Bitcoin the end game? Bitcoin is so cool. It really provides the properties of safety and liveness, and we can now have this self-regulating currency. And the answer is no. It is good, but it's not good enough, because Bitcoin is secure only under synchrony, but not under partial synchrony, because whenever there is any partitions, then this 51% guarantee is gone. And also, it confirms blocks with some error probability as a function of k, but it never finalizes block. It also has an energy problem, because proof of work, as you probably already know, is burning a lot of fossil fuels. One question from Sangu. Why does it have a significant difference between the number of incoming connections and outgoing connections? Okay, about the peer-to-peer networks. Oh yeah, Bitcoin's network topology, we've been working on this for quite a number of years. Bitcoin has 8 outgoing peers. Actually, it now has 10 outgoing peers because of our own research. We actually proposed it to increase it to 10. So now 10 outgoing connections and 115 incoming connections. But still, number of incoming connections is a lot more. The reason is that in the Bitcoin network, where is it? Oops. In the Bitcoin network, in many other blockchain networks, if you actually look at the networking layers, you will see a small number, relatively small number, like 16,000 servers nodes that receive connections from anyone, okay? And as I said, there are a lot more nodes that never accepts connections, but to make connections to others. So we call them a Bitcoin servers, and there are many other Bitcoin clients which are not visible yet, visible well, because they are not visible because you cannot really make connections to them. So that's really the reason that they receive a lot more incoming connections than making outgoing connections. They're serving the community in some sense. Okay, it's a peer-to-peer connections, but they provide more services than receiving services. So it's a little bit of imbalance that you see here. Okay. So energy issues. We all know that Bitcoin is burning more energy than some countries like Netherlands and Israel. And there can be attacks. Even 51% is a pretty good property, right? If you want to attack Bitcoin, then you need to somehow convince more than 50% of people, miners, in terms of hash powers. But oftentimes, from time to time, we see that a one or two small number of mining pools can actually have more than 50% of hash powers. But as far as I know, as far as people know, we haven't seen any attacks that 51% attack yet. The reason is probably is that maybe it's not visible or not so frequent, or they also do care about the security of it. Miners also care about the Bitcoin's price. When there's any weird thing happens, then price goes down, then that's something they don't want as well. So they just would follow the rule. That's probably the reason, and that's why proof of stake actually makes sense after all. So in other words, the attack might not be rational after all, but there's no guarantee for the future, of course. So with that, I think we can have a short bathroom break, because we have covered the digital currency from the very simple scenario where 3-person tries to have a self-regulating coins and slowly build up to have this problem that we want to solve. And we have seen how Bitcoin kind of solved it. And everything was kind of informal, but I hope that you got the idea. So now we understand blockchain, at least very early version of blockchain. And now we're going to move on to Ethereum, and we're going to have a 3-minute bathroom break.